So without further ado, I'll get into what's new in the past 2 weeks in vLLM with 0.9.1. We had over 270 commits from 123 contributors, pretty good ratio, and 27 of those were brand new contributors to the project, so shout out to you in the community. As I mentioned, sort of the highlights are really a lot of progress on large-scale serving. A lot of the push there has been on combining data parallel attention with expert parallelism. There's been a lot of, we supported this feature for a while, but we've been doing a lot of optimizations, such as integrating the DeepGem and DPP kernels more closely, adding CUDA graph support, and adding new MOE kernels to optimize the performance there. For disaggregated prefill, we've added support for heterogeneous tensor parallelism, so the prefill and the decode workers can have different amounts of tensor parallelism between each other. Pretty complex. The KV caches are different sizes, so it's non-trivial. And then data parallelism especially has seen a lot of support from a basic feature into supporting interoperability with many other features. So good stability there. And then, we've had simplification to setting up the kernels, optimized kernels for expert parallelism, like the Perplexity kernels and the DPP kernels from DeepSeek. We've simplified this and made this much easier, so you don't need to build like GDR copy from source and things like that. A key attention backend that's been in the crockpot for a while is FlexAttention from the PyTorch. We're really excited about this for being a very flexible PyTorch-driven attention implementation that gets torch compiled into a very efficient implementation. So we expect this will allow us to support many new attention features in vLLM v1 faster than we would be able to in more compiled attention libraries like FlashAttention and FlashInfer. And then also support for optimizations for RLHF workflows, as vLLM is used more in those, and continual work towards supporting non-uniform KV caches as we start supporting more state space models and models with local attention, where we're working on the hybrid memory allocator. As a key model support for this release, Magistral from Mistral was a highlight, a new reasoning model from them. We had day 0 support for that, and various enhancements to other models. Some documentation updates. Please let us know if you like the new documentation or if you have edits there. And then, a whole swath of hardware support. So as I mentioned before, we have a variety of work on NVIDIA Blackwell, on supporting new FP4 precision, supporting CPUs, AMD ROCm, Power CPUs, TPUs, Neuron, you name it. But some of the highlights I'll mention is we've had a lot of tuning on NVIDIA Blackwell, so those new B200s you're getting your hands on. We're starting to reduce overheads there and look to see the 2x performance boost from H100 to B200 that you should expect. And then, on the ROCm side, we still see a lot of support, a lot of work on pushing DeepSeek performance there, which is great. And then also, not to mention the CPU backend finally having support for the V1 vLLM engine, which is great for some of the CPU users out there. And then on TPU, I'll mention the addition of single process multi-device worker execution is a new paradigm to vLLM that's key for good performance with Torch XLA. That is cool to see from the TPU folks. And then in terms of engine features, we finally added compatibility between LoRa and Beam Search, which is a feature requested by some users. And we've reworked some of the server logging to allow users to better customize and prune unnecessary logs. That's basically that there. Please make note of some of the API deprecations. We now have, I think a month ago, we defined a sort of formal deprecation policy, and that once we mark things as deprecated, we aim to actually remove those in 2 releases. So these are planned deprecations that have met their time. So make note of those. And that's all we have for this release. please feel free to ask questions in the chat, and we, of course, will have a Q&A at the end. But without further ado, I'll hand it off to Carlos.
Great. Hi, everyone. Just share my screen here. Okay, I hope you guys can see this, so I can actually drive. All right, so yeah, I'm Carlos Costa, Distinguished Engineer here at IBM Research. I drive a lot of the innovation agenda for hybrid cloud for AI. I work very closely with Red Hat, our business units, and also with the community. I'm seeing some kind of familiar names here. I come from a large-scale compute background, HPC, but more recently really kind of pushed the boundaries around Kubernetes for some of these specialized workloads, right? So I'm very excited to talk about LLM-D. This is super close to this community, so thanks so much for the invite to speak here. This is just a start, so I'll do like an introduction, touch on some of the motivations why we're doing LLM-D, and also engage in a conversation. Feel free to ask questions. We can take these in like different directions. But I mentioned Kubernetes, and I actually wanted to just start to kind of some, I don't know, level setting on some context, right? Because scaling inference is very different than scaling traditional workloads, right? And while we have very solid, proven ways to scale, say, the backends for HTTP requests, right, and kind of microservices, very well established in Kubernetes. But inference is, of course, very different. You guys know this very well. But the problem really is that unlike HTTP requests, they're very fast, uniform, cheap, right? They don't carry like any state, say like a KV cache or anything like this. So there are like a lot of like load balances that were developed for this type of things that simply don't work for inference requests, right? And that's one of the problems, the fact that if you're doing like inference scaling, what I mean by that's, of course, multiple replicas, right? How you make decisions, for example, where you fulfill a request and so on, right? The problems of request routing, load balancing, right? Auto scaling, all of that, they're very unique and kind of break the traditional Kubernetes scaling. With LLM-D, instead of reinventing things from scratch, we actually build on top of some of these proven patterns and features in Kubernetes by extending them, and also build on some of like the new changes happening at Kubernetes, right? So you see that again, I mean, we're not kind of reinventing the wheel in many ways, we built from that. One of the key things for LLM-D as like a design principle is really how you deliver scale, performance with SLOs, right? Insurance SLOs, right? This is really for the users or the operators that they run a service, right? That comes with the requirements for quality of service, right? And how you actually have the knobs, of course, to do resource utilization minimization while you keep some of these requirements. Design principles, of course, like accommodate for heterogeneous hardware or like a hardware agnostic platform from the get-go. So I'll walk you through like how we're building this. So what I'll do breadth first. Okay, so I'll give you like the main components in LLM-D first, talk a little bit about them, and then I'll double click on each one. I'll spend more time on the routing piece because I think this is something that might be a little bit new to this community, but you see that, of course, underneath you're using like, of course, KV connector, well, of course, PD disaggregation is a big thing, very, very big one. But then I'll show like how we build a platform around these features, right? Again, feel free to chime in anytime. I think the design principle is here. But what I wanted to kind of to start with is just this idea of LLM-D. Of course, it's like the same space of other stacks, like recent ones, including Dynamo, for example, that I saw the question, that's why I'm addressing up front. There are many, of course, attempts to build and address this challenge. Some of them are very good. We are taking this path of starting really kind of centered on Kubernetes. And why we do this, right? So first of all, we don't want to reinvent the wheel in the sense of one of the challenges like operational complexity, right? So if you start to add a lot of like new things, this becomes very hard to operate. So our user here is really like the operator deploying, again, a service. This can be like 2 nodes all the way to thousands of nodes, right? So we start from like a building from parts that we know like scale and a good, so not reinvent. And one particular thing is the gateway API. This is, of course, something that's part of Kubernetes, has been around, but more recently, if you follow this community, something called the Inference Gateway or Inference Gateway extension has been pushing the community to just create better mechanisms to handle inference requests. So you can look at the body of the request, make better decisions. LLM-D, we build on top of this, show like how we actually extended this. We create better algorithms, for example, to schedule inference. And what we're doing basically is we got this request. We have a way to, of course, do body-based routing. And we do this based on things like prefix cache awareness, KV cache awareness. Those things, of course, are very good and pay off big in many use cases that I'll touch on. But we also, of course, do things like inference requesting based on TD disaggregation. Now, where we have two pods, or the preview or the decode, how request is done that way, right? So what are the new filters and scores you need when you're doing like the routing selection based on these characteristics, right? So this is like number one, what we call generally the optimized inference scheduler, right? That's a big chunk of LLM-D today. Number two is, of course, support for disaggregated serving prefix. So LLM-D is built on the KV connector, prefill decode disaggregation support. This, of course, comes very closely from this community, right? A lot of the things that got into the vLLM recently. And we do this from an orchestration perspective, right? And there are two ways to look at this. You can do shared prefix caching, right, with a pair, but also you can do independent prefix cache when actually offload to a cache storage, something like LM cache is what we're using, right? So if you look at left-hand side, the three kind of big dependencies that we leveraging on LLM-D, one is Gateway API, the other is Nixo from Dynamo, right? So we, again, as I said, don't invent the wheel. This Nixo is very good, of course, for KV transfer, supported fully integrated in vLLM. So we build on that. And then for caching offloading, we're leveraging LM cache today, more like a plugin. We can, of course, do different things here, but that's what we do today. This is very recent, okay? So the project's just 2.5 weeks old. It's getting a lot of momentum. I'll do a little bit of like a community time to check, because the other very important design principle here is that we want to build a standard with the community, right? So this is not about requirements from just like a Red Hat or IBM or the players, but it's really how we come together as a community to establish a standard to scale inference, right? So important, of course, the relationship with the vLLM community, because vLLM is very central to this platform today, as you guys can see. So this is really transcending beyond like a single vLLM instance, and LLM-D is the community response for how we do that, right? I want to touch on like a very unique value propositions in terms of like how we position ourselves, right? I mentioned one, which is just to like make it easy to operate. Again, we are building on Kubernetes standards. So for operators already kind of doing this in the field, it's not a big leap actually to operate LLM-D. We build on top of Gateway API. So this makes it much, much simpler. Flexibility from day zero, as you see, LLM-D runs already on more than one hardware platform, right? And it's very extensible, and it's also modular, meaning that some of these features that I touched on, they can be used independently, right? And then performance. The key things that you enable, I touch on the inference scheduler, on disaggregation. I also mention auto-scaling, okay? Because here now you have to decide many things. So you have to decide when to scale up and down based on like the inference request demand, right? And we also need to decide, for example, how many instances for prefill, decode, and so on. The auto scale is something that is happening now, right? So there's a lot of actual activity in the project for auto scaling. So I actually invite you guys to also join and follow some of the things that you're doing in that space, right? So I mentioned some of, again, the optimizations, and it's all about doing all of that while you keep SLOs. I'll give an example in terms of numbers, but just like as a teaser, right, with some of the features that I call out, if you're running like on the 2 nodes at top, like a 16 GPUs, with the routing pieces only, we're able to for example, deliver 2 times higher QPS within the same SLO. So that's important, right? So it's not like we're relaxing the SLO. And if you're able to relax a little bit, it can be even like a 3 times lower latency. I'll show like the details for some of these numbers, but just to give an idea of the low-hanging fruits that you have here. And of course, this can go even higher as we scale and go to, of course, more like specialized scenarios, right? We launched on May 20th with 4 founding contributors, 7 launch partners, and actually switched to that view because that's one of the key unique values of LLM-D, right? It really builds on this pain point across the industry around the inference scaling, right? In the context of, again, running a service. There are a lot of like projects that popped up, but I think we all felt like the need of one single big tent that we could bring all this excitement in the community. And LLM-D is the response to that, right? So as you see, some of like the names when we launched, it was great to see like all the blogs and activity around the launch with all our partners talking about this. So you see all the big names are there, including NVIDIA, AMD, right? The Dynamo folks also joined here, right? As being a dependency, Google is a great partner, being very active, is one of the core contributors as well, bringing the gateway, Inference Gateway as like a big component. We work very close also with CoreWeave, which is scaling some of this stack of the CoreWeave platform, right? So it's great to see this kind of initial momentum. But what is very important, right, and very good to see, we're just talking about the LLM community, and I'm happy to also tell you guys that the LLM-D community, as a, I don't know, like a sister community to this one, is also growing very organically. We're seeing very good uptick in terms of stars or like the metrics that we care about, but also very active engagement, right? So we already have like 6 in the LLM-D community, from like auto scaling to PD disaggregation, distributed KV caching, and all of that. So invite you guys also to take a look. And this is coming from a lot of like players, and some of this is it's very, very organic, right? People actually taking these and try out. One good thing to mention is that, again, unlike vLLM, where which we can just try out on a laptop, very easy. LLM-D does require like a Kubernetes cluster, can be some local thing, but again, it's really for the operator, and you've seen that there are enough people with paying that space and actually taking LLM-D for a spin. It's very early as well. I'll say that up front, right? While the features that I mentioned, they are there today. I mean, we're seeing some very interesting numbers for some of the routing pieces that we came out with. Some of the scaling for PD is still ongoing, right? So there is plenty of opportunity for the community to engage and also bring requirements and, of course, contributions, okay? This is kind of the, I don't know, the introduction. I'll spend some time double-clicking some key features, right? And if time permits, I'll go all the way to show some numbers as well, okay? Feel free to interrupt or ask questions anytime. I'm not seeing the chat, so if you want to chime in, just raise your hand, and I can interrupt and address the question, okay? So let's talk about some of the core features, okay? Sorry, getting some echo. Any question?
Yeah, is there also like page attention? There is an original paper for LLM-D?
We have LLM-D is like a combination of several components and techniques, right? There is a blog that kind of describes everything. So if you search for LLM-D, or if you go to LLMD.ai, you get reference for a blog where we talk about all of this. And then it touches on other reference as well that we link in the blog. I think that's the best place to start.
Thank you very much.
Sure. Yeah, so I always like to show this, like we talk about all these components and all this complexity in some way, and then of course the question is why I should care, right? So I'll lead with some of the target use cases just to make it clear. It won't be new to this community, but I want again to just call them out once again, right? So of course, one of the key problems that you're trying to address is the fact that you're seeing requests now with much more like variance in terms of size, right? And these emerge, for example, from RAG patterns, where we have, of course, like long inputs with prompt and the retrieved document and short outputs, or reasoning, where we have the other way around, right? Short inputs with long outputs. And these patterns, they cause a lot of like imbalance, right? When actually scheduling some of these requests. So, and this imbalance, of course, kills your ITL, right? So be able to do better optimized scheduling based on those patterns is, of course, what we're going after. That's one. The other is the fact that there's a lot of like caching opportunity, right? So in this community, of course, we all know the value of prefix caching, which becomes super common if you go to agentic patterns, for example, where many times you're kind of reusing some of the prefixes, right? So now what if you actually can do request routing based on prefix caching state, right? So imagine now that you have multiple replicas, you're caching things in different places. What if I can actually do the routing based on where I actually have the higher chances to get a hit, right? A cache hit. So LLM-D is also trying to address this, and I'll show you like routing based on prefix cache awareness, and you see how this actually becomes a very beneficial thing, even in a small setup and with one or two models. Okay. And I won't spend, of course, a lot of time on the prefill and the code disaggregation. This comment absolutely knows the value of this, and we're actually piggybacking on the support that was enabled in vLLM. Of course, we, broadly speaking, IBM and Red Hat, as you know, are being very, very involved. But once you have that support, of course, that's what we use to do a better location of these requests. As we know, this is what big names in the industry they're using to really scale, right? From Google, disaggregation of TPUs, great partner actually in this community, work very closely with us, all the way to, of course, DeepSeek using disaggregation to scale. The right-hand side here is something that it's important. I talked about SLOs. And when it comes to doing this in production, one thing that we should note is the fact that SLOs can be very different depending on like what you're doing, right? Depending on the workload. We can go from requirements for really ultra low latency when you're doing things like code completion and search. This really needs to be milliseconds, right? All the way, of course, to chat agents where like seconds are okay, or maybe like in email drafting, to moderate where like we can even tolerate minutes of latency for things like summarization or things like deep search and things like that. All the way, of course, to even hours if you do some sort of bad jobs, right? So being able to accommodate different SLOs in the same platform is what makes it very flexible, and also how we can accommodate more things, right? You can just like have a better efficiency if you have this type of kind of more heterogeneous workloads. How are we addressing this? Now I'll get more like into the weeds. I'll spend, again, as I said, more time on the routing piece. Keep in mind that, of course, we're using a lot of the PD, and I'll touch on that in a little bit, right? So there is this API in Kubernetes called Gateway API, which is like the ingress API when you're getting requests in a Kubernetes cluster and deciding where, of course, you're fulfilling that request, where you ship like and do computation. Gateway API is something that's been around for some time. It's an API, and there are different implementations of that. So the actual gateway, right? So the control and data plane, and Voy is one of them. The others like Istio Service Mesh and a few other things, right? So what those things do, they again help you with basically routing requests when you have like multiple instances of a service, right? The same, of course, happens when you have multiple model replicas where you have to decide of course, where to send that. So recently, a year and a half ish ago, there was this push to let's extend Gateway API to include support for inference request. We were part of this, and now part of LLM-D, we actually extended even further, what we call GIE, right? Allowing us to plug specialized logic for things like KV awareness and prefix and so on. And that's what you see in this picture. So it's a combination of changes to GIE, Gateway Inference Extension, and some logic for our own schedulers, right? So one of them, for example, is this indexer for KV cache score. So if you go to LLM-D, you see specific code for that. And also, it's a big one, it's the fact that now we can do routing based on the 2 pods, like for prefill and decode. So that orchestration that you can send a request to a prefill decode pod and orchestrate like the pullback to do decode, right? So that's also part of the inference scheduler that we added. Okay, we needed, a few additional things like the routing sidecar that goes with the vLLM pod that helps us to, again, decide when we do like a prefill decode and the orchestration. And I'll show an example like of the flow to make this a little bit more visual and all the steps that happen to get there. Okay, so this is the inference request routing. How you get all this stuff, right? So a big call out to the deployer. I'm sorry, this jumped a little bit further than I wanted. Yeah, so there is a deployer. So if you go to LLM-D today, there is an automated deployer. So what this will do is it'll basically configure a gateway for you. You set up the gateway endpoint, deploy the whole thing, and set up also some model replicas, right? There is something called model service, which is a very simple, opinionated way to deploy models that we do today. It was based on CRDs. Now it's a Helm chart. We're moving to a Helm chart. Similar in some way to K-Serve, but this is like a very lean approach. You can do your own way, so you don't have to use this. But if you go to the deployer, LLM-D, you get like this fully formed getting started package that you can just keep code apply in your cluster, and you get a lot of these dependencies. We're making this a little bit more modular to make it easier to consume different parts. We also now going with some of user stories, so user cases. So we're trying to just kind of create some blueprints for folks to just get started in a much easier way. Okay, let me show now what happens after you deploy LLM-D. Okay, and I'll make this like very visual for like one request flow, and then I'll show you a little demo, and then of course some numbers, right? So if you go and deploy, so if you use the LLM-D deployer, what you get LLM-D gateway, okay, an APP, an endpoint picker, and here we deploy 2 instances, one for decode and one for prefill, okay? And there is a Redis instance also running because we use Redis to keep some of our indexer, right? So now let's try to kind of query one of these models. This, I believe, is a Llama 4 model. It doesn't matter here, right? There's a prompt. I'll send a request, and what I get, so this hits the gateway and hits my endpoint picker. So what it does, it assembles the request, and then it goes through a bunch of filters, okay? And this happens very fast. I'll check, for example, do I have any information about the session? Is this coming from the same user or a different user, right? Have I cached any of the prefix? Do I have a KV cache already cached somewhere, right? And finally, do I want to actually disaggregate this request and do prefill decode to 2 different pods, or just run this as a single request, prefill decode request on one of my pods, right? So those are like the filters that you applied when we get the request. And for prefill in the code, this is opportunistic, meaning that there is a configuration for length of the request. If it's too short, then of course this adds more overhead than benefit. So you can actually tune that. So you can basically make it like for very long, and then you can define long with disaggregate. For short, we just go straight to the decode. This is also opt-in, right? You can do the other filters without prefill decode, right? So you can tune your way. So here we got the request. We go through those filters. Prefill decode is enabled. Then I check the length of the request. I decided that I'm actually running this prefill decode disaggregated. So I send this to my prefiller. The prefiller again check. I'm sorry. This is the sidecar, right? As I said, I'm using sidecar to kind of gate some of these requests. I'll check for if I have any caching. In this case, I don't. So I invoke KV cache is loaded. I'm actually basically now I ran through the prefill. I'm loading this in my LM cache, and this of course goes through NIXO and LM cache, and then I actually now schedule a decode pod, which does a pull to do the other end. I decode and I get my request complete. That's kind of the overall flow, and I'll show like in a little demo. So this shows like everything at play. I check for caching, I check for if I do prefill decode and go all the way. Because I want to show some numbers for just the routing piece alone, I'll show a demo that we do KV cache aware routing, okay, in isolation. So in this scenario, we have 3 users, okay, and they'll come with user 1 and 2. They'll come with identical system prompt, but different user prompt, and user 3 have a completely different one, right? Different both system and user prompt. So what I want to see from the system is that user 1 and 2 should be routed to the same pod to maximize KV cache reuse because they share the same system prompt, whilst user 3 would be routed to a different pod for load balancing, okay? So if you look at this, I'll play a little video, so just to show in action. Let me just let it load a little bit so it don't get blurred. Okay, so system 1, I'll just make this big, I'm sorry. If I can, I don't, okay. So chat 1, given system prompt, I'll run the prompt. There is no cache, so it first populates the KV cache, and this takes 3 seconds. Okay, and then you see the actual request. So this is what my EPP looks like. So I'm running a scorer. I don't know if you see my cursor, but because there is nothing about this request, I get like no cache hit. Scorer comes out null. So now I run the chat 2, same system prompt. I'm telling, hey, this is same user, different user prompt. So there is some reuse here. So you see that I'm actually now running this request less than half of the time because I actually able to send that request to a place where I already cached the prefix. So here you see things coming. I have a scorer that produce some number. That's a high score. It kind of adds the affinity to run on the same pod address, right? And then let's see what happens with chat 3. System prompt, user prompt, these are completely different ones. It will take on like three seconds because this is running on a completely different pod now. I'm loading balancing here because there's no cache hit, right? Of course, this is very simple, but then just to give you, there's another one, of course, if I just now repeat chat 3 with the same prompt, but just change the user prompt, this will be naturally be sent to that third pod that I cached chat 3, right? So you see that again, it's just like load balancing plus cache awareness at play, built on top of very solid features like the Inference Gateway plus the scores and plus the logic to do so, right? So why we should care about this, of course, right? Let me show some benchmarking numbers. Some of these are in the blog. We're still in the process of benchmarking a lot of these features. So it's actually an invitation here to the community to also take a look and share feedback. But this is what happens when you're running LLM-D on 6 nodes. Eight 100 GPUs. This is like a fairly like old cluster. I'll show some numbers on H200s as well. But this one is running Llama 370B struct. Of course, here you see the traditional curves for QPS. ITL versus QPS, and then TTFT and throughput, right? We go all the way from 0 to 20 QPS, which is somewhat like not super high, but high, right? And of course, the traditional curve, which is the blue one here. So you're running multiple replicas, you're doing just round robin, right? If you just deploy this on Kubernetes, that's what you get, right? Out of the box. Again, just doing round robin, and what often happens is basically saturating very quickly, right? So here the red line shows what happens when you're doing KV, cache aware, and load aware scores, and you see that you basically have this much better close to flat lines because we're hitting some of those nodes again and again. The same happens for TTFT, and then for throughput, it's the other way around, right? So if you're doing a good job, you don't saturate, continue to scale up to a point, and this is also some of what we're seeing here, right? I also want to show this in the context of SLOs. So this one shows the scenario where I have basically like 2 mods or 3 scenarios, okay? Scenario 1, I'm deploying a Llama Scout TP2 to replicas, right? So this is set up with 2 nodes, 8 H100, so multiple replicas of the model. So scenario 1, I don't have any SLO, right? I'm not trying to keep this like envelope. Scenario 2 and 3, I do want to know like how well I can do within a latency envelope. So like, let's say P95 less than 2 seconds, right? Because as you guys know, end of the day, that's how you, of course, sell a service. So that's how, of course, you guarantee like the user experience, including like a long tail type of thing. So scenario 2, it's again a Llama 4 Scout FP8 to TP2 for replicas, right? And very, very long input length, short output length, okay? For both scenarios. And then as 3, it's older model, Llama 7B for replicas, again, looking at like an SLO envelope, okay? Looked at, again, I mean, note that here we're trying to really stress KV cache reuse, reason why we have this super long input, just to kind of give an idea of the benefits that you get. So what you see on the graphs, again, it's both TTFT versus QPS, right, like before. And what you see here is like, what is that kind of SLO threshold? So the dotted line, both S2 and S3. And the way to look at this is like how much further in QPS you can go while still kind of below this line. That's what we're looking for here. And then the takeaway again is for Flash 1, if you look at these curves, you can go all the way to like a 3 times lower TTFT, which of course is better here. But for the scenarios 2 and 3, where I'm trying to just see how much demand I can fit within an SLO, LLM-D delivers 50% higher QPS for that SLO, P95 below 2 seconds, right? For Llama 4 scenario, Llama 3 scenario, 2 times the baseline. So compared to round robin, right? Under the same SLO. What is the takeaway from these numbers, right? It's actually very simple. Is doing twice as much with the same hardware, keeping the same SLO, which is, of course, it's a compelling value proposition. This is a small scale scenario, so of course we're doing a lot of the larger scale exploration as well. But that gives you an idea of what routing based on KV cache awareness, load awareness, and prefix can do for you, right? And all of this again build on top of things that folks already use in the field, build on the cutting edge of Kubernetes technology, and also helping to evolve the Kubernetes itself to better accommodate this type of workloads. I hope this makes sense. Again, feel free to chime in. I know that you're kind of starting to run out of time, so I spend just like a minute on next steps here. So then we can open for questions. I mentioned about early scaling. That's a big one. That's work in progress. So now using a lot of what I just described, you're going after SLO-aware early scaling. So basically deciding again when to spin up pods, what type of pods, how many of them, right? Including the PD scenario, right? So that's something that is happening, how this is integrated with the inference scheduler. One very big goal for this project is scaling large-scale MOEs, right? So with things like PD plus encode parallelism, decode parallelism. So that's a big thing that is happening now. A lot of activity in that space. There are many other things that I call out here, but there's a lot of work also in benchmarking some of this, right? Especially for PD. I didn't show any numbers for PD here, because this is something that is happening now. So with our contributors and partners, right? Actually, we're pushing this to a large scale. We're also going after DP-aware load balancing strategies as well. You're also extending GIE with the ability to kind of bring even more like advanced schedulers. And we have the express goal of doing more detailed benchmarking in the coming weeks. Highly recommend and invite you guys to check the repo. We also have a Slack for LLM-D, which is becoming very active. So please stop by and also join us there and try the deployer. So you can actually try this out on your cluster today. So once again, thank you for the invitation to speak here. I hope that was a good introduction. There's a lot that we can double click. We can do that in some of the questions, but also offline, either here in the vLLM forum or over on the LLM-D Slack. So thanks a lot.
Yeah, thanks a lot, Carlos. I think that was a really great overview. There's definitely a lot of questions that have been popping up in the chat that I've been trying to keep up with along the way. So we can kind of go through some of those, but also if people want to come off mute and ask questions themselves, feel free now. Oh, sure, go ahead, Doug.
Hey, thanks. Appreciate it, Carlos. That was very interesting. Question. Okay, so a number of the examples that you showed how, all right, you're going to get a query and then it's going to get it to the right place for, say, that pod on, this host running this LLM. Does it also cover scenarios where you would have like a distributed serving of the models themselves? Like say you've got a super large model and you use something like a Roy or something like that to distribute it. Does it also try to automate that kind of scenario as well?
Yeah, no, great question, right? So yeah, so I should have said that. So today we support models that fit in a single node, right? So the routing that I described can be like many replicas, but all like a single node. So multi-node support, if you have like any level of parallelism, right? And that's like my second bullet here, actually. So doing like MOEs that goes beyond like what we can fit in a node. And the short answer, this is something that is coming to LLM-D as well, but this is work in progress right now. I hope that helps.
Awesome. Yeah, no, that helps. I want to ask more questions, but I want to give other people a shot. So thank you. Appreciate it.
Sure. Yeah, anytime. Right. Yeah, maybe I can look over some of the questions here. Oh, there's a lot.
Yeah, we've kind of gone back and forth quite a bit. I'm trying to scroll back up.
Yeah, I don't know, Michael, if you can help me. Like,
are there plans to host any LLM-D meetups?
Yes, no, that's a great one. Yes, we actually do have a community call, right? So every Wednesday, I think the plan is to have some kind of meetup soon. No from plans yet, but we've seen a lot of activity in the SIGs, as I said, the community calls. I think we have enough critical mass to do so. No plans yet, but something that we're considering and would love to do. Yeah.
Yeah. One question I thought was interesting, kind of up, was, yeah, is LLM-D working on any fast cold start auto scaling optimizations?
No, great questions, right? You guys are just amazing, like how you just spoken, like in the exactly the things that you're going after. Yeah, all these auto scaling piece that I described, right? I think the immediate question is like, hey, but that only makes sense if I'm able to bring up things quick, right? A bunch of things. So one thing is how fast you can just load the model itself, right? So there is work, for example, just bypassing some of the layers, doing things like GDS straight to NVMe, right? That we can load just like data transfer quick. The other one is, of course, sleep mode in vLLM. So you just keep things like pre-warmed, if you will. So all of these, of course, are things that exist, but combining this with an autoscaler that factor in the time to load the model is how we can do like some interesting optimization for startup, right? So short answer, this is part of the broad autoscaling work stream that I mentioned. And there is some work in the community, both with sleep mode in the LLM, combined with some library to load the models faster. Straight from the storage.
I had another question on that, Carlos.
Sure.
Do you know, like, what technique you intend to use for that monoloading? Like in some discussions I've had with NVIDIA people, they've thought of using Nixel even for monoloading, not just KV transfer. Because you mentioned GDS, which I've worked with a decent amount, and I'm curious if you're using QFile or using some other implementation to get there.
Yeah, it's actually QFile. So this is, yeah, exactly. So we started some of this before Nixel, right? So we when I say like we IBM Research, something that you bring it to the project as well. We made some changes to Hugging Face Safe Tensor Library, right? To actually include some of the CUDA calls directly. Nixel is a great abstraction, something that, as you notice, we already use, and some of our NVIDIA friends are also part of some of the work that I'm describing here. So I think it's natural that we start to leverage more of the Nixel implementation, but this is all kind of ongoing, and I actually invite you to join some of these discussions and maybe help us to kind of nail some of the design directions for that, right? But ongoing work right now, and I think Nixel will play a role as well.
Awesome, yeah. Michael mentioned that he was maybe going to start a discussion in vLLM or something around it. So
yeah,
it'd be great
I mean, there's a lot
to
of
hear more on the cold
within
start.
vLLM that yeah, like we just need to improve the startup time. We've kind of we compile too many CUDA graphs. We use Torch compile too much. We do too conservative like peer-to-peer checking. We can easily speed up the vLLM start time within itself, even agnostic of model loading and things like that. So yeah, definitely look forward to improvements there.
Great.
Yeah, well, we're basically at the last minute, so definitely thanks everyone for the questions. Please feel free to follow up with us in the LLM-D Slack or the vLLM Slack. We're happy to forward and answer your questions there. And of course, go to the GitHubs themselves, post issues, ask questions on issues, ask questions on PRs. Open source is driven by like interest and importance of users. So you are the users, and we want to know what you care about, and if we're not caring about it enough. So thanks everyone for being a part of the vLLM community and having interest in other communities like LLM-D. Yeah, hope you have a great rest of your week and happy building. Take care.
Thanks everyone. Bye.